So it turns out that the way that the magnetic force works gives us a way to figure out the sign of mobile charge carriers. And also for certain specialty applications, it allows us to figure out what the electric current is through some substance. So let's start by imagining that we had absolutely no idea what the sign of charge carriers were through some material. So we could just take a guess that possibly the charge carriers are positively charged. And this is indeed the case with human nerve cells, or actually just nerve cells in general, where the charge carriers are positively charged potassium ions. So this is a realistic situation. So let's say that we have a conventional current that is flowing from left to right. So let's imagine also that we've just turned on a magnetic field that is going into the screen. So we'll break this up into two time periods here. So over here, we'll take a look at what's happening initially. And then over here, we'll take a look at what happens after we've achieved steady state. So initially, if we have positively charged ions as our charge carriers, if the conventional current is flowing to the right, which way would our charge carriers be drifting? Yeah, they would also be moving to the right. So we got our positively charged carriers. They are drifting to the right. So I want you to work out the right-hand rule here to figure out which way these positively charged charge carriers would be feeling a magnetic force from our magnetic field that is into the screen. Yeah, the magnetic force would be up. All right, so we can think about what that's going to mean for the path that our charge carriers will follow. They're going to curve up. Then what's going to happen when they get to the end of our conducting strip here, or just our strip of charge carrier? Yeah, they literally don't have anywhere else to go. So what's going to happen is you're going to the mobile positive charge carriers would just crash in here. And similarly, you would end up leaving behind negative charge carriers that were stuck, negative charges that were stuck in the lattice because they're bound to the lattice, because we're assuming positively charged charge carriers are mobile. Okay, so with time, you're going to be building up a surface charge along the top bit here, and usually when you're doing this, like to figure out something about a material, usually you make this into a strip. So we'll just imagine that's a strip. So now I want you to ask yourself, which way will there be an electric field pointing in our strip? Yeah, we'll end up building an electric field that's pointing down. Now we're going to build up charges until such point as the influence of the electric and the magnetic forces cancel out. So if I have a positively charged charge carrier here, Which way is it feeling an electric force? Yeah, it's feeling a downward electric force, and we already worked out that it's feeling an upward magnetic force. Now, if we're in steady state, here, let's just go ahead and continue to label our drift velocity here. If we're in steady state, we need the two of these to be equal. So we demand that the magnetic force be equal to the electric force. So here, this is going to be QVB sine phi, and I'll just leave it as a sine phi. The way I've drawn the example, phi would be 90 degrees, but there's no reason we couldn't have the magnetic field lines going in obliquely or something like that. And the electric force would be equal to Q times E. Now here's the interesting bit. The charges cancel. And we get that the speed of our particle is E over B sine phi. So particles will keep crashing into the wall here and leaving behind charges here and building up an electric field until such point as the electric field strength is this to perfectly balance it out. Now, usually so you can even do this as an intentional effect. If you're wanting to pick out charged particles of a specific velocity, so usually you'd be saying phi equal to 90 degrees. Maybe you're working in a vacuum or something like that. And you would have V equals E over B. And this kind of arrangement gets called a velocity selector, because only particles that are moving at this exact speed will pass through straight. But let's get back to our looking at our conductive strip here. So because we've got an electric field here, this means that across from the top to the bottom of the strip, you're going to have an electric potential difference. This usually gets called the Hall potential. And so I would want you to imagine if you were to put the black lead of a voltmeter on the bottom end of the strip and the red end of a voltmeter on the top of the strip, would the voltage that you read be positive or negative? Yeah, it'll be positive because remember, voltmeters always read red minus black. And this is a higher voltage here, and this is a lower voltage here because electric field lines always run from high to low. Now we can repeat this entire process for the case where our mobile charge carrier is negative. So again, we will have our conductive strip here. Now, instead of, say, this being a nerve cell or something, might just be a strip of copper or something. So again, same deal. We're going to divide the strip up to look at initially and steady state. And so let's go ahead and say that we have a conventional current flowing to the right. Now, if I have negatively charged charge carriers, which way is their drift velocity going to point? Yeah. Remember, conventional current goes opposite the direction of negative charge flow, so the drift velocity would be to the left. So again, we will imagine that we have a magnetic field that is going into the screen here. like so. So now you have a negatively charged particle moving to the left, and you have a magnetic field pointing into the screen. Which way is this particle going to be feeling a magnetic force? Yeah, it's actually going to be up again. Remember, because the particle is negatively charged, you flip your index finger to point against the direction of motion because negative times left is right. Again, as a result of this force, these particles are going to curve up, then they're going to crash here, and then they don't know where to go. So this is going to dump negative charges here and leave behind immobile positive charges down there. So eventually we'll get to a point where we build up negative charges on the upper surface of our strip and positive charges on the lower surface of our strip. So which way is the electric field going to run inside our strip? Yeah, it's going to run up because it points from positive to negative. So again, it's the same deal here. We're going to look to have our forces balance. So here is our negatively charged particle. It is moving to the left. And we worked out that the magnetic force is going to point point up. And remember, since the electric force is F times QE, since E points up, but we're timesing it by a negative number, the electric force will point down. And again, as the surface charges build up, this force will get greater and greater and greater until the ratio of our electric and magnetic fields is at our velocity selector ratio. So again, we're going to go ahead and end up with a Hall potential across our strip. So if I were to put the black lead of a voltmeter at the bottom of the strip and a red lead at the top, what sign would I read for the voltage? Yeah, you'd read a negative number because, again, it always reads red minus black. Since electric field lines run from high voltage to low voltage, this is a lower voltage minus a higher voltage will give us a negative number. So this is how we can figure out the sign of our mobile charge carriers. If we go ahead and set up a Hall experiment and we measure a positive Hall potential, then we know that our mobile charge carriers are positively charged, like they are in a nerve cell. If we set up the experiment and we get a negative Hall potential, then we know that our charge carriers are negatively charged. By the way, this is also how you can measure currents in situations where it would be too hazardous to do it by breaking the circuit and inserting a meter. For instance, in certain healthcare scenarios, doctors sometimes need to know what the current is flowing through a nerve. Now, these currents are way too small to be able to use a clamp type ammeter to figure out what the current is, so that's a complete non-starter. So what they will do is they will go ahead and put whatever body part has the nerve in question into a magnetic field and very carefully touch micro leads to each side of the nerve. By measuring the Hall potential, they can figure out the electric field strength. Since they know the magnetic field already because they applied it, That gives them the drift velocity, and from that they can deduce the current going through the nerve. And so that way you can do it without breaking the nerve. Obviously, it's still a very delicate thing, but sometimes you need the data. All right, so in the next video, we're going to start taking a look at what happens when you have your charges, your moving charges are a current of charges moving through a wire. We'll catch you over there.